right, so I'm a big fan of JavaScript, and I'm an even bigger fan of compiling to it. Our next speaker is a middle school award-winning singer, a PM on the MS Edge team, and will be exploring the ecosystem of transpile to JS languages and how it will affect the future of the web. Everybody give it up for Patrick Kettner.
Hey everybody, like Ken said, my name's Patrick, and I am a program manager on the Edge team. I do a lot of outreach work and get to kind of research cutting edge technologies. And of course, I work a lot with JavaScript, but I'm not actually kind of really here to talk about JavaScript itself today, ironically, considering the conference. But I love JavaScript, to be clear. I've been on the web for a really long time. I learned how to make a website on Lisa Explains It All. Hands up if you got any old schools. No? Oh man, you missed out this outside. Hey, this site was amazing. This was when I was in elementary school. I was lucky enough to have a really well-funded IT program when I was young, and so I got into on the web in '95. And what was kind of uniquely awesome about being on the web that long is that you get to see trends happen over time. For example, you go from really educational sites that aren't incredibly well written, table layouts, if you remember, to more, the Ajaxification of the web several years later, DHTML that came with IE 4 and 5, to the standard stuff that came with the Wired News redesign, where it turns out we didn't have to write everything in tables. Or when mobile phones happened and we all started talking about responsive web design for the very first time and thinking about how you didn't need to have a static 960 pixel design. It was mind-blowing at the time. And of course, kind of now the hot thing is progressive web apps. And it's starting to really make us rethink what can even go into applications. What can websites or web apps really be? How can we push the boundaries even more as we continue to move forward? And like I said, I get to work on a browser, and so I spend a lot of times figuring out how that's possible. And a lot of what that ends up meaning is really reducing bugs. And I spend a lot of my time in apps like this. This is CodePen, of course, which I'm sure we're all familiar with. All the time get sent over bugs on major websites, whether they're progressive web apps or even just random things that people want to work that aren't working in our browser. And I kind of just slowly reduce those pieces of code over and over and over again until it can be the smallest amount of broken stuff that I can send to our engineers so we can make it better. And so I spend a lot of time in tools like this, and I love it. But the one thing that always kind of frustrated me as much as I loved it was this right here. It's the fact that a lot of my demos, when I'm writing them myself, I end up using SCSS or sass under the covers. And sass is awesome. It completely changed the way that I wrote CSS. It changed the way I think about CSS. I think a lot of us do. A lot of us, that's the case, rather. But the problem, if you're using a site like CodePen and you're trying to work on an airplane, is that sass is in Ruby. Excuse me. And if something's written in Ruby, you can't run Ruby in the browser, and so you can't have an offline version of CodePen, because if you try and upload your SCSS to a server, it'll just fail, and you'll be really sad, and everything sucks. And that really sucked for me. I was thinking about how we're living in the future for so much of the web platform today, but when it comes to something simple like just a website's functionality working, like CodePen, something I love very deeply, it just was broken. I couldn't get it to work. And I spent a lot of time thinking about this, and I eventually found a way to make it work. It's a project called Opal. Now, to be clear, Opal is not a project that I wrote or created. My team didn't create it. It's an existing one. But what it is a source-to-source compiler. It takes, and what a source-to-source compiler is, because I didn't know what it meant at the time, is that Opal takes your Ruby code, does stuff to it, and then it outputs JavaScript. If you're familiar with Babel, how you can kind of take ES6 code and rewrite it in a way that's ES3 code, that's also a source-to-source compiler. It just happens to be JavaScript to JavaScript, different versions. Opal takes Ruby, converts it to JavaScript. So I didn't come from a CS background at all, so all of this was completely new to me. I apologize if this bores any of you guys, but I'm just going to kind of go over how that's even possible. Three main steps in how that works is Lexing, parsing, and code generation. So the very first step of that is Lexing. Now, what Lexing is, it's also occasionally called tokenization, is literally starting to scan your file character by character and breaking up pieces of code that it recognizes. What does the programming language actually understand? Things that you wrote that make sense. If you ever have a syntax error or some kind of problem where your cat runs on your keyboard, Lexing would generally break. So at this point, we've basically broken up this really simple piece of code into saying, okay, we see a keyword, an identifier, a couple of integers, etc. Each one of those individual pieces are called tokens. Now, the important thing, the difference between Lexing and parsing, is that at the Lexing step, While that code was valid, this code is also valid to Lex. Even though it's completely nonsense, it wouldn't run in any JavaScript environment at all, it still Lexes. All the Lexing is doing is recognizing individual pieces of code as valid pieces of code. The actual assigning of value or assigning of meaning to those individual tokens comes at the next step. That's the parsing step. So what parsing does is it goes through each one of those tokens in the order that you put it in, the order that you wrote it in, and actually starts to understand what the heck you're trying to do in your code. In this case, obviously, we're trying to set a variable called sum assigned to the number of 1 plus 2. Fairly straightforward. Now, the last piece is kind of the most hand-wavy. It's basically just taking that raw concept that has been figured out by the parsing step that ensures that your code is actually valid, and it starts to output the actual code that's being generated. So we will take that concept and start to build out what kind of is like this tree-like structure right here. In fact, you might have heard of these things before as abstract syntax trees or ASTs. Basically just means a way to represent the logic of your application or your code inside of a tree-like structure. And once we have 2 tree-like structures, one for JavaScript and one for Ruby, we're able to kind of compare them and output that Ruby code. It's a way to translate between the 2 languages. Those ASTs are incredibly powerful, and that's what powers Webpack, Babel. A lot of our modern front-end tool sets are powered by ASTs. So again, that's what makes us have this kind of a piece of JavaScript code and then rewrite it to Ruby, though this particular case wasn't difficult to figure out. When you're dealing with something like Sass, which is a 10-year-old project with hundreds of thousands of lines of code, it's a lot more complex than deleting the keyword var. So, so now that I generally understood what that even meant, I decided to just kind of dive in, created a file called Opal sass. This is a Ruby file, and first of all, I required Opal. This was, again, the thing that converted Ruby code into JavaScript code. I added Opal parser. The Opal parser is what allows you to take strings at runtime. So since, again, we're going to be compiling Sass, we need a way to take in your Sass code at runtime in the browser, so we need a parser. That parser comes from Opal. We're requiring it here. Next up, we require Sass, the library, as you would imagine. And then finally, we have a function. We're just calling Sass builder. It takes in a string and an options object. The string is just literally your CSS. Your options object is just a whole bunch of boring stuff I don't need to get into here to configure to make sure that your Sass is the exact kind of Sass you want it to be. And then we just pass that to the internal API that Sass uses to output CSS. So fire up my terminal, call Opal, and holy shit, it didn't crash. So I felt really proud of myself. I was feeling really good because this was like an hour into me figuring this out. Opened up and made a really simple HTML document and went to open it up in the browser, and it was immediately crashing. It didn't do anything whatsoever, and that brought me to my first rule that I learned whenever I am transpiling JavaScript, is that it never works. Well, the first time. Inevitably, like I said, this is a 10-year-old project, Sass. Opal is a couple of years old, but neither of them were ever written. Sass wasn't written to run in Opal. Opal wasn't written to transpile Sass. Inevitably, there's going to be some kind of a rough edge that needs to be sanded down in order to get it to work. The whole point is, if you ever try to do this, don't get discouraged just because it doesn't immediately work. You'll probably get it pretty straightforward. Now, one thing I didn't mention up until now is I've literally never written Ruby before this at all. I've installed Ruby. It took me a couple of days, like Kim mentioned, but eventually I got it working. And it was there, but I have no idea. So this error message is undefined method, match size for class. I'm aware of classes in ES6. I still don't understand how to read. I just copy and paste from the React docs. And otherwise, I don't know what any of this really means. But what I do know is that generally speaking, if something gives you a string as output, you can probably grep for it. So I opened up Sass, and I just grep for that class. I have no idea what any of it means, but it turns out it only shows up in one file. So more than likely, my problem is going to exist in that file. So I dig into that file, and there you go. It's a class definition, and it says there's a comment right above it that says a wrapper of the native string scanner and a whole bunch of other stuff. And I'm like, aha, a native string scanner. So that probably means that native means it's coming from Ruby, more than likely. So more than likely, Opal is messing something up here. It's trying to transpile something that should be in there, but it's not. So I dig into the Ruby docs. Turns out, yep, that's completely true. It's a built-in. And it turns out Opal just doesn't support that feature. So number 2 is that the tools aren't perfect. Opal is a continually evolving project. It's not guaranteeing 100% Ruby coverage, but it is just code. It's something that, if you spend some time, you'll be able to understand. Just like you can dive into Webpack today, it's all these tools are made by people. You're also a person. You can figure this stuff out. And so, again, fire up grep, go over to the Opal repo, and start looking for where they're defining string scanner. Pull it up, and I have no idea what I'm looking at, because this is written in Ruby, but I just kind of dig in. There's some definitions for functions. Def in Ruby is how you declare a function, or the equivalent of a function. They have one called beginning of line. They have another one called scan. These are all built in. These are things I recognize from the Ruby docs as being built-ins to the native things that should be extended. And then inside of each one of them is just this string. All they do is return a string. And you might notice that there's some like blue syntax highlighting of like POS right there, or working, or different pieces that are kind of a little bit brighter. And it turns out those are Ruby variables that get injected at compile time into the JavaScript string. So all Opal does is that you figure out the logic of what that Ruby method is trying to do, and it outputs JavaScript that does the same concept. So every single thing is just little tiny JavaScript that keeps getting injected into the page that it theoretically runs the same logic as your Ruby code. So after scanning the whole file, I confirmed there was no match size function. So I just looked at the logic of what it meant to be, and I submitted a pull request, and match size is now a part of Opal. And it wasn't that hard. All it was doing was match size is just returning the length of the most recent match. It's fairly short. You have a variable that is the most recent match, so all I had to do is return that dot length, and that was it. All of a sudden, I knew Ruby. It was great. Yeah, I knew less code when I started professionally programming, so I was really proud of that. So anyway, I fixed that. I recompile. I have my changes made to Opal locally. This is a day or two later, and I open up my dev tools, and hooray, the error is gone. It actually compiled, and I was feeling extremely cocky at that point. I decided to fire up the command. You might have a hard time reading it, but this is basically just the JavaScript that needs to be run in order to get the result from Opal internally. And it's just a really simple CSS. All it is a single class that has no styles, and it immediately crashed. And that brings me to rule 3. All of this is extremely tedious every single time. It never goes away. Whenever there are errors, it's never like, holy shit, this entire concept completely doesn't exist in a language. It's like, oh, you forgot a semicolon. And it's a lot of those it's the death by 1,000 cuts that will really kind of prevent you from doing that. So like I said, don't get discouraged, because you can probably figure this out. It just takes a lot of footwork. And a key thing to remember that makes this a lot better is just simplify whenever you can. So this particular error, the 2-symbol error, ended up eventually, I figured out that was actually a problem that needed to be changed in the Sass code. Symbols are a thing in Ruby that can't really be translated directly into JavaScript exactly, but you have similar ideas in Ruby that can be converted to, and so I just had to modify the Sass code in order to get it to work, and it worked identically the same. If you're keeping track, I have changes in Sass, I also have changes in Opal, and not to give you a spoiler alert, but eventually all the gem files and dependencies of those projects have to have changes too. And that's a lot to manage. God forbid I accidentally RMRF a file, or I have to do something, I lose all those tiny little semicolon changes. It's a huge pain in the butt, and it's a lot to mentally handle. And I'm not that smart of a person, and so I'd rather I let tools do these sort of things. And so I pulled up Opal Webpack. Sean Larkin recently joined the Edge team, so we're legally required to use Webpack for everything. And I mean, notice. And I'm not really doing much with Webpack in this project. All I'm doing is exposing the Webpack lifecycle. And what I mean by that is that I have access to the file right before it's transpiled and right after it's transpiled. And so there's all these little tiny changes I have to make right before it's given to Opal to convert it. And so what I end up doing is using my favorite loader, string replace loader, to effectively just do a regex over the file. And I know regexes are gross, but regex can also literally be just the exact string you want to replace and the exact string you want to replace it with, and that works too. And that's all I had to do. So this is horrible for a screen, I apologize, but basically this is just a whole bunch of statements where I slightly change the exact string that exists to a concept that can actually be written and run, and there's several hundred of these. I actually crashed PowerPoint with the length of this GIF, so it's much shorter than it is in reality. But there's a lot of little tiny changes that had to be made. And eventually, I got this. You go to offlinesass.club, and it's a horrible website that looks like this. And it is, let me see if I can pull it up. Yeah, and so you can do stuff like change this to red, and then hit compile, and holy shit, the whole thing recompiles. The entire Sass lifecycle exists inside of a web worker. It'll go offline. I'd go offline, but it takes time. But trust me, it's offline, and it all works in a web worker. So a site like JSBin or CodePen or any of these other demos can now run the entire Sass library inside of a web worker offline. That means that you can have all these demos as a PWA. You can have it locally while you're on a plane or while you're in an area with poor Wi-Fi. Usually a conference is terrible, but actually this conference Wi-Fi is the best I've ever had. So my joke no longer works here, but holy shit, thank you for formidable people. It's seriously better than my apartment right now. But yeah, so anyway, I was feeling extremely good because I had something that finally worked and I was still alive. And so I tweeted out a tweet that said, check it out. And of course, immediately people told me how it was broken and stupid and I needed to quit my job. And that brings me to rule 4. And that, of course, is test everything. But the cool thing about this is that when you're transpiling from Ruby, if y'all aren't familiar with the Ruby community, they are obsessive about testing. They test everything almost all the time, especially major projects like Ruby. And so, the kind of sub-corollary to that is that reuse whenever possible. Like I said, it turns out they already had hundreds of thousands of assertions inside of all their tests that test every single combination of Ruby you could basically possibly imagine. It's nearly a decade old, the project, and so they figured stuff out. They know what to do. The only problem is that all of these tests are written in Ruby, obviously. Those don't run in the browser. That doesn't help me, and so I actually had to hand rewrite every single one of these assertions into JavaScript in order to get it to work. That took a long time, but I have a lot of free time. And so eventually it actually works. And what's great is that if you check it out, all those dots are individual test files, and there's a bunch of hundreds of little assertions inside of each one of those dots, and it works. And because we had used that kind of framework, the Webpack and the regexes to replace stuff, it worked for all of those versions of Sass. I could go back in time and build every single version of Sass that's ever existed since the concepts of gems were created, and it all worked. They're all automatically generated. That's 7 years of Sass. I've been saying 10, but that's because Sass existed before inside of Haml. But that worked too. It's just way too much work to extract it from an internal gem, and no one cares that much. I'm just showing off at that point. And yeah, so now I have this command called grunt generate Sass, and I run that, and it builds all 80 versions of Sass. I hit that command, and then I go walk my dog and take a nap, and eventually come back, and Sass is built. It's awesome. It runs the full test suite. Everything functions in a browser in all major browsers today. It's awesome. The crappy part, if anyone can guess, is that it says 2.7M, which of course is 2.7 megabytes of JavaScript. Now, I know the average website is now like 3 megabytes of JavaScript, but the average website is not just the Sass runtime inside of your JavaScript. And so that's kind of a problem, right? It is 2.7 megabytes, but even the most compressed version of Brotli you could possibly do, where I had to put my laptop inside of the freezer to keep it from exploding while it was running, it's really, really, really big. 250 kilobytes, is tiny, it's still gigantic. And even then, the parsed version in the browser is going to be megabytes already. You can't run that. You can't really make that any better either. I mean, I work at a browser, but I can't magically change stuff. And that really frustrated me, but have hope, because there is a future to how we can transpile stuff to the web and how we can have it really effectively, and that future is WebAssembly. Now, in order to explain WebAssembly, I kind of have to inception a few layers in and explain ASM. ASM.js is a somewhat recent addition to JavaScript, I think 5 years or so now, and it was created by this guy, along with a lot of other people. This is Alon. He currently works at Mozilla. At the time, though, back in 2010, he was a game developer. Now, there was a major change in game development, especially mobile game development, around 2010. Does anyone remember Steve Jobs' Flash, how it was dead and everything never running on the iPhone? And so he had a blog post about how that was kind of scary, because all of a sudden mobile gaming might be in danger, especially on the web. And that's how a lot of people still access games on the web, or games on their mobile phones, is through the web. And so he wanted to bring better gaming that didn't rely on Flash to the web. So he wanted to port a project that he'd been working on called Bullet Physics. This is a render from Bullet Physics. It's actually won Oscars and Emmys and all kinds of technical awards for its power, because it's super impressive. And he wanted to be able to have that style of rendering in JavaScript. And so, this is a C library that he had created. And so in order to make that happen, he created a tool called mscripten. In order to explain mscripten, I have to dive in again. I apologize. This is the bottom level. This thing called LLVM. LLVM, that is their actual logo, is low-level virtual machine. And the idea of LLVM is kind of similar to what Opal was doing, only much better. So just like before, Opal kind of rewrote your JavaScript into your Ruby into JavaScript. What LLVM does is it has a front end and a back end. The front end takes in languages, usually C++, like in this demo, and it outputs usually bytecode that runs, on your processor. So LLVM powers the Chrome build pipeline right now. If you ever try to build Chrome from source, you'll use Clang and LLVM internally in order to do it. In order to make sure it runs on your device, whether it's a mobile device or a laptop, it has different backends in order to output to those processors. But in this case, LLVM will go over your C++. It converts it into bytecode that would normally be a different font that is supposed to look better. And then mscripting comes in as a backend, and rather than output bytecode that runs on your processor, it outputs JavaScript. outputs a really, really specific version of JavaScript, and that thing is called ASM. So ASM, zooming back out, what makes it more unique compared to what Opal outputs is that there's actually a standard behind it. Opal right now is just a couple of people that write random strings that get output into the browser and into your compiler process today. There's nothing standard about it. I submitted a pull request, they had no idea who I was. You know, working in standards at a browser, it's much more bureaucratic. And what's great about the type of creating standardized output is that browsers can make it so that they can optimize this output as much as possible. You might be wondering, keep in mind ASM is just JavaScript, but it's JavaScript that no one should ever write. This is the pretty output from ASM. It's not the unminified thing. And it's basically just filled with a whole bunch of really crazy tricks that can tell the processor and the parser, rather, you know, your V8, your Chakra, your JavaScript engines, how to run this really, really fast. There's a ton of them in here, but one example is this guy right here. This is sort of pipe 0. And what that trick is doing is, I can't remember the word, I apologize, but basically it's forcing anything to the left of that pipe to be an integer. If it's not an integer, it converts it to 0. And so take, for example, this piece of code, x plus 2. If you were a parser and I told you what is x plus 2, there's no way to know that automatically, right? X might be a string, in which case you take x and then you put 2 after it, so it'd be literally x2. It could be an object, in which case you have to stringify it and then add it to 2 again. It's a concatenation thing. Or it could be an integer itself or a float, in which case you do actual mathematics, right? There's no way to really know that. And you know, JavaScript engines are really dumb. You're much smarter than them, and if you don't know this, it can't know it either. It just does it really, really fast. And so what we can do here is if we add this horrible code that you should never write by hand, but it's okay to be produced by tools, x will definitely always be an integer, and so it can skip all that logic check. So if I tell you what's 0 plus 2, you can tell me probably immediately it's 2. You don't have to have all this kind of weird questioning inside, and the engine can do the same thing. It can reduce a whole bunch of checks it has to do and make really, really fast code. And this really fast code can actually be performant and run today. There's some amazing use cases for ASM already in the wild. There's SeattleJS, which is a full version of MySQL and SQLite that can run inside of JavaScript in a web worker today. You can have a full database today, and it works. It runs great, runs at full speed. Another one that's great is Quake.js. It is literally a full version of Quake 3 ported in JavaScript running in the client. You can run death matches. Let me see if I can pull it up. Yeah, I'm really bad at Quake, but Ken Wheeler threatened me earlier to a death match. But yeah, you can run at 60 frames a second, you know, connecting over WebRTC. All this stuff is amazing, and it's through ASM. It runs in the browser. It's great. Not only that, you can have entire operating systems. This is Windows 95. There's that recent hoopla about MS Paint being killed. Well, as long as you have a browser, it can live on. And you can run it inside of ASM today. Like this stuff works. This has been working for years. Just people honestly don't really even know about it. Not that you really need to run Windows 95. But still, it's amazing what we can do with browsers today by transpiling, by bringing these other languages and this rich history of stuff to the web. And you know, you might be remembering, though, that this is all ASM. And I was talking about how WebAssembly is the future. And so why is it the future? Why is it even better? So comparatively, remember that all that ASM stuff, like I said, is just JavaScript, right? It's just a huge string file that gets sent down to the browser. It still has to be lexed. It has to be parsed. It has to have code generation. What WebAssembly is the binary representation that comes out after code generation. So basically, rather than shipping down a string file that every single time has to be parsed and lexed and generated code, you ship down the code that has been generated, and immediately. So as soon as it can be downloaded, it can be run. So all the steps that have to go on with ASM code can be skipped. It usually means that it can boot up to 10 times faster than most ASM code in the wild today. Not only that, all of the code can automatically be hot-pathed. So if you've ever had a de-optimization in your JavaScript performance analyses, that won't happen because you're always in bytecode inside of WASM. It's really great. It also gives the language designers a new target to add features to. There's all kinds of crazy stuff being added to JavaScript, like typed arrays or other things that probably don't help most web developers. But with WASM being its own binary target separate from it, they can add new features there specifically just to be able to port C++ or other languages to JavaScript and never expose it in the JavaScript that you and I write. So it's a really interesting future. And you might be asking, how does this affect you? Like, it's cool, but you're never gonna, you have to get paid for a living, right? No one pays people to write Quake 3 anymore. Take, for example, React. Of course, it's kind of changed the way that most of us write front-end applications. in one way or another. And React ultimately is built on top of that concept of virtual DOM, which is, of course, if something changes and you compare two different states, if something changes in your virtual DOM, then you send over the diff to your real DOM so that you have the smallest amount of changes possible. It's basically just a way to be really performant on how to modify your DOM as good as possible. And this idea has been abstracted into a lot of different libraries, one of which is the virtual DOM library. You could imagine a world in which virtual DOM or React or other future libraries could be written in C++, in Rust. Mono just announced today the .NET alternative that they're outputting to WASM as well. You can write all of these algorithmic concepts in whatever language you want and have it run in the browser. So you can have these things parse faster than JavaScript, even though it's a completely other language, because it's written and output to WebAssembly. It's a really, really amazing future. And honestly, it's a really amazing present. You can check out the ogv.js. It's the OGG video format. It's a free and open source video format that isn't in a lot of browsers. Firefox was the big proponent of it. Edge is hopefully getting it in the future. Don't quote me. But at the moment, we don't support it, and neither do a lot of other browsers. But Wikipedia actually requires all videos be OGG. If you ever upload any content, it has to be an OGG Vorbis format. And as a result, they actually use a WebAssembly or assembly version, or ASM rather, version of JavaScript to parse the video file, output it to a canvas and an audio element. So if you ever play video on Wikipedia, it's already using a WebAssembly or an ASM version of a video codec. And you probably wouldn't even notice. It's really performant. It runs really fast. It's great. Not only that, I assume most people have used Facebook before. And I noticed something interesting when I was uploading a file, a photo a couple of weeks ago. They were downloading a JavaScript file specifically when I go to upload a file, upload a photo, and I decided to kind of dig into it. And I noticed that there's this thing called provides module ljpeg. And provides module is just a syntax inside of Facebook's code that means they're importing an external module. And what ljpeg is libjpeg, the C++ engine that controls all JPEG coordination. And it turns out what they're doing, from what I can figure out from their code, they're actually loading the entire libjpeg inside of a web worker so that when people try to upload like 50 megabyte photos or really giant raw photos, they resize them on the client. So you don't have to worry about uploading a 200 megabyte photo. You can convert it down to a 2 megabyte photo locally without having to go over the network, and it works. And this turns out this is something they've been doing for a long time. This is not new technology, and this is not something you should think is crazy or far off. This is something that's been happening today. You can really, really push the web forward with really straightforward ideas. Just think about all the different ways we've been doing computer science for 20, 30, 50 years, and you can bring it today. And that's my final rule, is just try something stupid. Like if no one thought that Elan could bring Emscript into fruition, the idea that you could write C++ code and have it run at all in the browser, let alone faster than JavaScript, it was insane years ago. It wasn't supposed to be possible. The fact that you could run, not that my contributions are anything close to that, but the fact that you can run sass in the browser is really dumb, but it helps me personally. I travel a lot and I spend a lot of time on planes, and it's really great to be able to not have to take 30 seconds per update on CodePen. It's really, really awesome. So yeah, that was me. My name's Patrick Kettner. Find me anywhere. I'd love to talk. Bye.